Question 8 of tutorial 4. Let us assume that L is a non-zero real number. In this question, we're supposed to show for this differential equation, along with two given values, so you can see this is a boundary value problem, we show only has the trivial solution y equals to 0 when lambda in our differential equation is 0 or when lambda is less than 0. Then we consider the case when lambda is positive and we want to find the values of lambda that give us non-trivial solutions. As you can see from our differential equation, the trivial function y equals to 0 is indeed a solution to this differential equation. Let us begin. We'll consider two cases. When lambda equals to 0, you see our differential equation simplifies to give us this. The characteristic equation is just u squared equals to 0, which implies u, the root, equals to 0. We only have a single real root. Using the key theorem, so both these exponentials disappear. They are 1. E to the 0 is 1 in both terms. Therefore, the equation, the general solution, simplifies to give us this, a polynomial, a linear equation, c1 plus c2 times x equals to y. But if you have a straight line and two of the points on the straight line are 0 or give you 0 at two different points, it means the line itself is constant at value 0. So you can check. Indeed, we get in this case y equals to 0. That settles the case when lambda equals to 0. Let us move on. When we look at the case when lambda is negative, we can write our differential equation in this form. When lambda is negative, we have that plus lambda equals to minus the absolute value of lambda. So this is the differential equation that we should get. We take a look at the characteristic equation, and here we see that these must be the roots. As you can see, these are real roots, but they are both not equal to each other. So the key theorem tells us, and the general solution is in this form. When x is 0, y equals to 0. Substitute that inside, and it tells us c1 plus c2 equals to 0. We also have y at x equals to L equals to 0, and therefore we get this equation. Here is where we substitute x equals to L and y 0. We solve for this and we get this expression. When I multiply by e to the square root of absolute value of lambda times L, it cancels away this term and I should have 1. I should get this equation. What else do I know? C1 plus C2 equals to 0. What this means, therefore, is that C2 equals to minus C1. So I substitute that inside here and I produce this formula. So now I can draw an inference that C1 equals to 0, and if C1 equals to 0, then because C2 is minus C1, C2 is equals to 0 as well. Why is it true? Let us assume that this other term, e to this power minus 1 equals to 0. This is true if and only if I have the exponential equals to 1. But this is true if and only if when I take the logarithm on both sides, ln of the e allows me to bring down equals to ln of 1. It's just 0. L is supposed to be non-zero, and lambda is also non-zero. Something non-zero equals to 0, which is strictly speaking impossible. Therefore, this term is never going to be 0. C1 is the term which has to be 0, and therefore C2, based on what I have, is also going to be 0. Therefore, y equals to 0. In other words, we have shown that the only possible solution is going to be the trivial solution. This solves part A for us. Now let us consider what happens when lambda is positive. In this case, we can consider this differential equation. We find the characteristic equation and we find the roots. Because lambda is positive, the roots, they are complex numbers. So we have to use case number 3 of our key theorem. But notice the real part of both roots is 0. We only have an imaginary part. Therefore, in our formula for case number 3, the exponential term doesn't appear. Now we use the given values. When y is 0 at x equals to 0, we substitute, and it shows C1 equals to 0. When x equals to L, C2 times sine of square root of lambda times x, which is equals to L, equals to 0. Now if I have the case given here, what I don't want is for C2 to be 0, because if C2 is 0, it just gives me the trivial solution again. So I must have C2 not equals to 0, but sine of square root of lambda times L 0. When does this happen? Let us take a look. When the sine function equals to an integer multiple of pi. So if we have that square root of lambda times L, whatever is inside the sine function, is not equal to n times pi, which means the lambda is not equals to the square of n pi divided by L. We can divide by L because L is non-zero. Then this is equivalent to sine not equal to 0. But that means in our formula C2 would have to be 0, and then we would have the trivial solution. Therefore we see we get non-trivial solutions only when lambda equals to the square of n pi divided by L, where n is allowed to be any integer of our choice. We have infinitely many integers, so this shows us that we do get infinitely many non-trivial solutions. Hence, in this case, when lambda equals to square of n pi divided by L for a fixed value of n, the solution becomes what we get here by substituting for the value of lambda. C1 is 0, so this term disappears, and here we should get C2 times sine of square root of lambda. Here is lambda. When you take the square root, L is just stated to be a non-zero number. It could be negative. And if it is negative, we will need to be careful because we are squaring a negative number. So when we take the square root, we should have the absolute value of L instead. Why don't we have a problem with pi? Because pi is a positive number. And also here you can see we should also be careful with n, because n is an integer but there are also negative integers like -2, -3. We must remember that we are squaring. So when we square, we are eliminating the minus sign. But when we square root, we need to remember that it is going to give us the absolute value. That is why we'll have here sine of the absolute value of n times pi, which is always positive, divided by the absolute value of L times x. This is the general solution for the case when lambda takes such a value, which corresponds to all those cases where we do get non-trivial solutions, or rather when we can get non-trivial solutions. If there are such solutions, we must have lambda in this form for some integer n, and the solution is given by this form. And this solves question 8 for us.